we're going to look at implicitly written equations versus explicitly written equations. So an explicit written equation means that I can tell that the equation represents a function explicitly. So what I mean, like, here's an example of an explicitly written equation. Okay. So typically they're solved for y so that I can see if I put in an x value, let's say I put in 4, that's going to output only one answer. Okay, so if I put in 4, 25 minus 16 is 9, square 9 is 3. I only get 3. No matter what x value I put in, I'm only going to get out one answer out of that. So every input maps to exactly one output. That makes it a function. If I look at this function, it is written explicitly because it's y equals, but now I see that if I plug in 4, I can get out an answer of 3 or negative 3. And so that input maps to two outputs, which means that's not a function, but I can tell very easily because it's written explicitly. Typically, they're written y equals something on the other side has only x in it. The stuff on the right side of the equal sign has only x. So we say y is written as a function of x. On this guy, I can't really say as a function of x because it's not a function. But typically when you see explicitly written equations, they are functions. I also want to mention that the difference here, some people think like, well, when I square root on this last step, you should get plus or minus anyway. This is called the principal square root. When the square root's already in the equation, you assume that they mean the positive version only unless they ask for the negative version. So if they put a negative, then they mean the negative version only. If they want both, they have to tell you they want both. So the one that's just written like this, it's called the principal square root, and it means we want just the positive answer, and that's what makes it a function. Okay, implicit equations are different. They're typically not solved for y. It's not y equals. And x's and y's might appear throughout the equation in different spots, mixed together, multiplied together. So we're going to look at how do we apply calculus to even these types of equations. How do we do the derivative? So the first thing is we're going to use this alternate notation. We're not going to use the f prime. We're going to use the dy dx. It lends itself to a little better understanding here. And remember, this means the derivative of y with respect to x. So it's about it's about the rate at which y is changing with respect to x. A change in y over some change in x. Remember, it's still related back to slope. So let's think about how we differentiate this equation. This is explicitly written as a function of x. I've got y equals, and then everything's written with x's only. We've figured out a bunch of rules on how to take derivatives of functions that are explicitly written. So we've got a rule for this one, which is chain rule. We're going to apply the power rule to the chain rule. So y prime, the 1/2 comes down. Recopy the inside, reduce the power by 1. Here's the part we're forgetting on the quiz. There's an inner function of 25 minus x squared. So we're going to multiply by the derivative of that inner function. If I simplify, the 2 and the negative 2 become a 1 and a negative 1. So we've got negative x over the square root of 25 minus x squared. And I'm going to use this dy dx notation instead of y prime. All right. Now let's look at the implicit form of that equation. Now it's not, well, let's just look at this. It's a circle centered at 0, 0 with a radius of 5. This is really, since we want a function, this is really only the top half of the circle. The bottom half of the circle would be the negative square root version. Okay, but we have to just look at one half or the other when we're doing explicit differentiation. that's the kind of nice thing about implicitly. I can look at the entire circle here now and take the derivative. So if I want to take the derivative of this thing, let's think about, we're taking the derivative with respect to x of both sides. Let me do this. That's how we're looking at this, okay? So the derivative with respect to x is going to be, I've got two terms here, so I can think of this. Whoops. I wanted to stay color coded here. X squared plus y squared equals 25. So the derivative of x squared is 2x. The derivative with respect to x is 2y. So y is not a constant here. Y, we're considering y to be some other variable that's changing as well. So the rate of change, or the derivative with respect to x of y squared, is 2y. But since we're doing it with respect to x, we have to apply chain rule here. And the inner function is going to be just the y. So we're going to say that the 2 comes down to do power rule, but then I have to times the derivative of the inside. And since y is a variable different than x, it's changing with respect to x. So the derivative of the inner, we're going to put dy dx. And remember, this what represents y prime. So we're finding the derivative when we find dy dx. Also, on the first one, you could think of it like this. The derivative of x squared is 2x, and then the variable here that's changing is dx, right? X is changing with respect to x. The bottom is always with respect to x, so I always make the bottom part with respect to x. The top comes from whatever variable I just took the derivative of, and that's the one that's changing. So again, this is an application of chain rule is how we want to really look at this, where the inner function here is just x. The inner function here is just y. So I take the derivative of the outer, 2x, times the derivative of the inner. So the derivative of x means x is changing with respect to x. The derivative of y is changing with respect to x. Get rid of all this stuff. All right. Now, I don't have to show, I want to do this part, and the derivative of a constant is 0. I don't want to show, or don't have to show, that the dx when I take the derivative of an x with respect to x, because that's just 1. So it's going to be 2x plus 2y times dy dx equals 0. Now, if I want the derivative, I want to solve for dy dx. So I'm going to subtract 2x off of both sides. Divide by 2y on both sides. And this is my derivative of an implicit form of the circle. That means this can represent the slope of the tangent line at any point on the circle. You'll notice that the derivative could have an x and a y in it. So now if I say find the slope of the tangent line at a certain point, I need to give you the x and the y. So I don't know points on this circle. What was the circle? Radius of 5 centered at 0, 0. So I know that 0, 5 is on the circle. So I could say, what's the slope of the tangent line at 0, 5? So if I plug in 0, 5, I get negative 0 over 5 is 0. I have a horizontal tangent line because this is a circle centered at 0, 0. So 0, 5 is up at the top of the circle. I get a slope of 0. Here's the cool part. We're going to have vertical tangent lines as well on these. It will be possible. So if we look at, and even likely, if we look at the side of the circle there, that's what, negative 5, 0. If I plug negative 5, 0 into my derivative, I get negative 5 over 0. That's an undefined slope. So I know that this tangent line is going vertical because I know the graph. If we look over here at explicitly, I could show you how these two things are equal. If I come back to here, I can plug y back in for that, right? That's equal to y. So that would really be negative x over y, just to show you that this thing works and we get the same derivative. We wouldn't do that really for explicit functions. We would leave them like this. It's easier to just find it with respect to like just having only an x in it. All right, so let's look at an example. So we want to consider this circle. Now, this one's not centered at 0, 0. Please recall that the equation of a circle is x minus h squared plus y plus 2 squared. 25. Whoops. I'm already doing that. Sorry. I'm already putting in the values. Equals r squared. So h and k is the center of the circle, and r is the radius. Recall that that's the equation for a circle. So it looks like this center is right here, which is 3, negative 2. And it looks like the radius has a length of 5. So our equation is going to be x minus 3 squared plus y plus 2 squared equals 5 squared. Okay, I'm going to multiply this thing out. So let's say it's presented as like this. You can start doing the derivative implicitly here, x and y mixed up on the same side. But in this case, since they're only squared, it's probably easier to multiply them out. So x minus 3 squared is x squared minus 6x plus 9. And y squared is y plus 2 squared is y squared plus 4y plus 4 equals 25. And then I can start bringing over my constants. If I subtract 9, I get 16. Subtract 4, I get 12. So then I'll get x squared minus 6x plus y squared minus 4y equals 12. Now, from here, I could take the derivative implicitly. So you just go term by term. So I'm not going to write the d dx for each term, but you would do this kind of for each term. So the derivative of x squared with respect to x is 2x times dx dx. The derivative of 6x, negative 6x, is minus 6 times dx dx. Plus y squared is 2y times dy dx. Minus 4, the derivative of 4y is 4 times dy dx equals 0. This is all because of chain rule. It's the derivative of the variable, always with respect to x in these. X is our independent variable until I tell you otherwise. Okay, so now we want to solve for dy dx. These equal 1, so times 1 goes away. I notice I've got 4 terms. Whoops, that's the term there. Any term that doesn't have dy dx in it goes on one side of the equal sign. Any term that does have dy dx goes to the other side of the equal sign. So I'm going to leave these two on this side of the equal sign. So I've got 2y times dy dx minus 4 dy dx equals 6 minus 2x. The reason I need all the dy dx's on one side is so that I can common factor out a dy dx. Now I divide both sides by 2y minus 4. And I could simplify. I could factor a 2 out of the top and a 2 out of the bottom. They divide out. I get 3 minus x over y minus 2. When I did this before, I got a plus 2. Maybe I did it wrong the first time. Let me just check my work here. Oh, right, up here this is a plus 4y. So this would have been a plus 4y. So that'd be a plus. That's 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 a plus. All right. So this is my derivative for any point on the circle. I now know the slope of the tangent line. Let's complete this table below. So my derivative is 3 minus x y plus 2. And they want it at the point 0, 2. So if I plug in my 0 and my 2, Whoops. I get 3/4. They want us to draw the graphical representation as well. I don't have a straight edge, but let's go to the point 0, 2. And if I draw my tangent line, there it is. And that's a slope of 3/4. All right, so now we go to 3, 3. I plug in that point. So I'm going to get, well, I'll write out my derivative each time. So I get 3 minus 3 over 3 plus 2. I'm getting 0 over 5. If I go to the point 3, 3, that's right here. I can see that I have a horizontal tangent line because my derivative is 0. I want you to finish the rest of these. Pause the video here. Okay, so here are your answers. Let's note this guy here. This is the notation we can use. You're going to say, you're telling me that you're going to evaluate dy dx, the derivative, at the point 8, negative 2. So we write a straight line. We write dy dx, straight line, and then we put our point that we're going to evaluate here at the bottom of that line. Remember, this looks like your n-derived format on the calculator. Right? They say we're going to take the derivative of d dx of, say, y2 at x equals 3, right? It writes this line. It's saying we're evaluating it at this x value. So you can write it like this. That's typically the notation. And we got undefined, and here are our other ones. Okay, so now we're going to practice the skill of taking the derivative of implicitly defined equations. They set the independent variable in the directions by saying with respect to x. So dx will always be on the bottom. So the derivative of this guy is 2y times the derivative of y, because it was a y that I took the derivative of, with respect to x, because that's what's on the bottom, equals the derivative of 2x is 2 times dx, because that's the variable that I just took the derivative of, with respect to x, plus the derivative of 3y is 3 times dy dx. This one is equal to 1, so to solve for dy dx, I got to bring them on the same side. So I got 2y dy dx minus 3 dy dx equals 2, negative 2, sorry. Nope, it's 2. It was already on that side. Okay, so then I factor out my dy dx, and I get 2y minus 3, and then I divide both sides by 2y minus 3. Okay, now we're going to look at our next guy and just keep doing examples. So the derivative of 2x is 2. I don't need to show my dx anymore if I'm just going to cross it off, so I'm not going to do that part. Plus, the derivative of an exponential is e to the y. Now the inner function here is the exponent, right? So it's y, so then it was times dy dx, because I took the derivative of a y, equals 2x, I'm not going to show the dx minus 2y times dy dx. I can't stress enough, that's chain rule. That's chain rule. That's where that comes from. It's the derivative of the inner function y. So now I'm going to get all the dy dx's on the same side. All the stuff that isn't dy dx on the other side. Factor out my dy dx. I'm doing a couple steps here. And then divide both sides by what's left over. So I get 2x minus 2 over e to the y plus 2y. Right? After I'd factored out my dy dx, I was left with this, and then I divided both sides by that. Okay, now I've got 2xy. This is a product rule. 2x is my first function, y is my second function. Right? So I've got one function times another. We have to do product rule. So the derivative of 2x is 2. Dx, which I'm not going to show, times recopy the second, plus recopy the first, 2x, times the derivative of y, which is 1, times dy dx, because I took the derivative of a y. This part can kind of mess us up. There is no y in this term, but it still has a dy dx, because I took the derivative of a y, equals 6y dy dx plus 2. I don't need to show the dx. I took the derivative of an x there. So if I clean this up, I have 2y plus 2x dy dx equals 6y dy dx plus 2. Get all your dy dx's on one side, factor out the dy dx, and then divide both sides by that. Simplify. So you should pause the video, do that right now, and see what you get. Welcome back. You should get 1 minus y over x minus 3y. Let's look at the next one. So I got 15x squared dx dx. Don't show that. The derivative of 3 is 0. Then the derivative of 2y is 2 times dy dx. And then I've got a product rule again here. My first is negative 3x squared. So the derivative of negative 3x squared is negative 6x. Dx dx I don't show. Times y. And then I recopy my first, negative 3x squared times the derivative of y is 1 times dy dx because I took the derivative of a y there. So I've got 15x squared equals 2 dy dx minus 6xy minus 3x squared dy dx. Gather your dy dx's and use your solving techniques to solve for dy dx as if it was a variable. You can pause the video and do that now. You should arrive at 15x squared plus 6xy all over 2 minus 3x squared. Okay, now we're going to answer some other types of questions other than just finding the derivative. So let's look at finding the horizontal tangent line. At what point on the curve is there a horizontal tangent? So we know that's where the derivative equals 0. So we're going to start by finding the derivative of this thing. So it's going to be 3x squared dx dx plus 3y squared times dy dx equals product rule. The first is 4x. The second function is just y. So it's going to be 4 times dx dx times recopy the y plus 4x, recopy that, times 1 times dy dx because the derivative of y is 1. And then we took the derivative of a y with respect to x. Plus the derivative of 1 is 0. So now I'm going to simplify that thing. So I've got dy dx. You can pause the video and simplify and see if you get this. 4y minus 3x squared over 3y squared minus 4x is our derivative. Now, when is this rational function? Right? It's rational function. Comes from ratio. Ratio means fraction, right? So just a little review there. When is a rational equal to 0? When the top is equal to 0. 0 over any non-zero number. So if I want to find what points, non-zero, if I want to find any points that make this equation equal to 0, which is what I want to do for my horizontal tangent line, I just have to worry about the top. Let's make the top equal to 0 and solve for either variable. I'll solve for y. Y seems to be easier to solve for here because it's not squared. So I add 3x squared, I divide by 4. So y equals 3/4 x squared. And then how do I solve this now? To me, it's a system of equations. I have an equation here with a y and an x in it. I go back to my original equation and I solve that system. It's two equations with two unknowns. So I already know what y is equal to. I'm going to use substitution. So I'm going to rewrite this now. I'm going to get x cubed plus 3/4 x squared cubed. I'm plugging that in for y here. Equals 4x times y, which was 3/4 x squared plus 1. Now I got to solve that equation for x. I'm going to say this is a calculator example. This is a good chance to practice. Put one side in for y1, the other side in for y2. You'll find out that x equals negative 0.770, and x equals 1.732. Remember, we always go 3 decimal places, and you put one equation, one side of the equal sign in for y1, the other one for y2, and they ask for what values of x, so I don't need the y values. However, if you did need the y values, you can go back to either equation that you used to solve your system to get the y. Looks like this one's going to be the easier choice, right? You plug those x's in, and you can get your y values if they wanted the entire point. Okay, so in terms of y, describe the values of x for which that curve will have a vertical tangent. So now it's the same curve, so it's the same derivative. So we got 4y minus 3x squared over 3y squared minus 4x. So a rational function, if I come back up to here, is undefined when I have a non-zero over 0. So now I'm just worried about setting the bottom equal to 0. So we're going to say a vertical. I'm going to explain our thinking. I should have written this above too, the same thing about horizontal tangent lines. Vertical tangent occurs when dy over dx is undefined, which means the denominator has to equal, I'll say would have to be 0. When I went to calculus camp, the guy there was from Kentucky. He was a nice guy, but he talked he had a little bit of a twang or whatever, a southern twang, and he would, anytime I say 0 now, I hear Tom saying 0. He says 0. Anyway, yeah, I want to always say 0. So I'm going to make the denominator equal to 0, and that would make my derivative undefined. So I'm going to solve for either variable. X seems to be the one that's easier to solve for here. So I subtract 3y squared, I divide by negative 4, and I get x equals 3/4 y squared. And I would then solve my system again if they wanted actual x or y values. But in this case, they just said in terms of y, describe the values of x, right? So there it is. It's done. I have x written in terms of y. It'll be for those x values. Typically, I'm going to want you to actually find the x values, so you have to resubstitute in up into solving this system, right? Plug that in for x everywhere, solve for y. Then once you get your y, plug it back in to get your x, since we want x values here. All right, so now we're going to talk about this. What does this mean? That actually means the second derivative. Okay, so we know that to mean the derivative of the derivative. So how do we do one of these guys? These are our last two examples. So let's get through them. So I start by finding the derivative. So it's 2y dy dx plus 2 times dy dx equals 2. So you want to solve for dy dx, and you're going to get dy dx equals 1 plus y, 1 over y plus 1. You can pause the video and see if you can simplify down to get that. There's your first derivative. So now I want to find the derivative of that. So now it's d squared y over dx squared. That's how we write our notation for second derivative. We're finding it's like you're thinking like you're finding d dx, right, of y like twice differentiable. So you can kind of think of it like that. So let's do what? It's going to be quotient rule. So it's the derivative of the numerator, which is 0, times the denominator, which doesn't matter because it's 0, minus, recopy the numerator, times the derivative of the denominator. So that's going to be 1 times dy dx, all over the denominator squared. So we have, let's see, we'll rewrite this as negative dy over dx over y plus 1 squared. Now, how do we deal with this? Sorry, d squared dy over dx squared. I know what dy dx is equal to, so I have to now go and make a substitution. so d squared y over dx squared, is going to be negative 1 over, what was that, y plus 1 over y plus 1 squared. So that's going to simplify to a negative 1 over y plus 1 cubed. Because this is like over 1, I multiply by the reciprocal. That is my second derivative. Okay, let's look at this guy. The derivative is 2x dx dx plus 2y times dy dx equals 0. So dy dx is going to be equal to negative x over y. Now let's find our second derivative. So again, it's going to be quotient rule. Derivative of the numerator is negative 1 dx dx, which I won't show, times recopy of the y, minus recopy the numerator, excuse me, times the derivative of the denominator, which is 1 times dy dx, which I do have to show, all over y squared. So I know dy dx to be this, so I need to substitute it in. I get negative y minus x times negative x over y, all over y squared. So I simplify by saying it's negative y plus x squared over y, all over y squared. I get a common denominator here of y in the numerator. So it's going to be an x squared, and over on this side be a minus y squared. So then I can rewrite these. I can like flip them around, so it's x squared minus y squared. So I'm going to get x squared minus y squared all over y cubed. Oh, I got a negative. This should be a negative x squared. Let's see where I messed up. This should be a plus here, because I'm doing minus, and then when I recopy, I consider the numerator negative x. So I'm doing minus for the quotient rule, and then times a negative x, because the numerator is negative x. So that makes that a plus, which makes this a minus, because the positive times the negative, which that minus then carries through. And there is my second derivative. So today we're just practicing this skill. We're going to look at how we can use it very soon in terms of a word problem or an application. So that is what's called implicit differentiation. How can you find the derivative when the x's and the y's are all mixed up?